Welcome back to AGRON Infotech. In this fourth clustering video, I switched to a cleaner and more suitable case study for time-based clustering. I used the Gapminder dataset, which is already tidy and perfect for teaching. Here, each country appears repeatedly across time, and that lets me cluster countries based on how their life expectancy changes from year to year. I begin by loading the packages. Tidyverse helps with reshaping and plotting. Gapminder provides the dataset directly. Per helps me repeat clustering across several values of K, and cluster gives me silhouette statistics for evaluating cluster quality. Now I load the Gapminder data and preview it. The output shows a clean structure with country, continent, year, life expectancy, population, and GDP per capita. There are 142 countries observed every 5 years from 1952 to 2007. Which means each country has a full trajectory across 12 time points. That is exactly the structure I need for this video. Next, I keep only the variables I need for time series clustering. I select country, continent, year, and life expectancy. I do this because the main analytical question here is not how rich a country is or how large its population is. The question is how the life expectancy pattern changes across time. Now I reshape the data from long format into a country-by-year matrix. Each row becomes one country, and each column becomes 1 year. This is one of the most important transformations in the whole workflow, because clustering works best when each observation is a single row with a complete feature vector. When I print the reshape table, I can see countries lined up against years, and that confirms the structure is now correct for clustering. Next, I separate the country and continent labels from the numeric matrix. I keep those labels because I will need them later for interpretation, but the clustering itself should use only the numeric life expectancy values. Now, I apply row-wise scaling. This is different from the usual column-wise scaling. Here I scale across each country's trajectory, so the clustering focuses on the shape of the life expectancy trend rather than the absolute level. This means the model groups countries that rise and change in similar ways, even if one starts lower and another starts higher. After this step, the quick output check confirms that the matrix is still in the expected country-by-year form. Next, I run principal component analysis on the scaled matrix. I use PCA only for visualization, not for clustering. The idea is to project the countries into 2 dimensions so we can later see whether the clusters occupy clearly different regions of the trend space. When I print the PCA coordinates, the output gives me 1 row per country with values for PC1 and PC2, which means the visual map is ready. Now I fit the first KMeans model with K equal to 2. Before doing that, I set the random seed so the clustering is reproducible. Inside the KMeans function, I set centers equal to 2 because I want to test a 2-cluster solution, and I set and start equal to 25 so the algorithm tries multiple random starting points and keeps the best result. This matters because KMeans can otherwise settle into a weaker local solution. When the K equals 2 output appears, the first thing I inspect is the cluster sizes. That tells me whether the split is balanced or whether one group dominates. I also look at the cluster means, which now represent average standardized life expectancy patterns across the 12 years. If one cluster shows consistently lower or flatter values while the other shows stronger upward movement, that gives an early hint about the kind of trajectories the model is separating. Now I repeat the same process with K equal to 3. Again, I keep centers equal to 3 and start equal to 25. The output now gives me 3 cluster sizes and 3 cluster centers. This lets me compare whether the extra cluster is capturing a meaningful new trajectory pattern or simply splitting an existing group into smaller pieces. Next, I visualize the K equals 2 solution in PCA space. In the plot, each point is a country. PC1 is on the x-axis, PC2 is on the y-axis, and color indicates cluster membership. When the graph appears, I can see whether the 2 groups occupy noticeably different regions. If the colors separate cleanly, that suggests the 2-cluster solution is meaningful. If they heavily overlap, it suggests the split is less convincing. Then I plot the K equals 3 solution in the same PCA space. This is where the clustering story becomes more interesting. The extra color shows whether the third cluster creates a clearer structure or just fragments the existing cloud. This side-by-side visual comparison is one of the easiest ways to explain how changing K changes the partition. Now I move into model selection using the elbow method. I set the seed again so the results are stable. Then I compute KMeans solutions for K from 1 through 10. For each value of K, I extract the total within cluster sum of squares. This quantity measures how tightly the observations sit around their cluster centers. As K increases, the total within cluster sum of squares always decreases, but what matters is where the improvement starts slowing down. When the elbow plot appears, I look for the bend in the curve. The steep drop at small k values tells me that the early clusters capture a lot of structure quickly. After a certain point, the curve flattens, and that is the sign that adding more clusters gives diminishing returns. Next, I use silhouette width as a second selection tool. First, I compute one distance matrix from the scaled country trajectories, and then for each k from 2 through 10, I fit a KMeans model and calculate the average silhouette width. The silhouette value tells me how well each country fits inside its assigned cluster compared with the next best alternative cluster. A larger average silhouette means cleaner separation. When a silhouette plot appears, I look for the highest point. That is the K with the strongest overall cluster separation in this run. Then I extract that value directly and print it as best_K. This is the value I use in the final model. Now I fit the final KMeans model using best_K as the number of centers and a stronger star value of 50. I increase and start here because this is the final model, and I want to give the algorithm even more chances to find a stable and high-quality partition. Then I attach the resulting cluster labels back to the country information and count how many countries fall into each cluster. That output gives me the basic size profile of the final solution. Next, I create one more PCA plot, this time using the final cluster assignments. This becomes the clean summary picture of the finished model. If the groups look compact and well separated, that supports the chosen K visually. Now I bring the cluster labels back into the long format Gapminder data, so I can interpret the clusters over time. This is where the time series logic becomes most visible. I group by cluster and year, then compute the mean life expectancy at each year within each cluster. When a line chart appears, it becomes the most important interpretation plot in the whole video. Each colored line now represents the average life expectancy trend of one cluster across time. If one cluster starts lower and rises steeply, another starts higher and stays consistently strong, and another sits in the middle, then the clustering has successfully captured different development trajectories rather than just arbitrary partitions. Finally, I add an optional continent composition chart. Here I count how many countries from each continent fall into each cluster. This does not define the clusters, but it helps explain them. If one cluster contains many African countries, another includes more European countries, and another is mixed, that gives real-world context to the trend patterns we just discovered. At this point, the workflow is complete. I start with a clean time series-friendly dataset, reshape it into a country-by-year matrix, scale rows so clustering focuses on trend shape, compare K-mean solutions, choose K using elbow and silhouette, and interpret the final result through PCA, cluster trend lines, and continent composition.